In this video, we will demonstrate how the Interactive Parallelization Tool, or IPT for short, can be used to parallelize an example that solves the circuit satisfiability problem. MPI stands for Message Passing Interface and provides a framework for allowing processes running in parallel to communicate with one another. We will be using MPI for our parallelization. Below is a snippet from the main function of this program that shows the hotspot for parallelization. This section of the code searches for the number of solutions by calling the function circuit value for each input. The evaluation of each input with the circuit is performed in the function circuit value, so the iterations of this loop are independent and have no dependencies on one another. This is a good for loop for parallelization. However, one should notice that the variable solution num is being reduced in this loop. This will need to be called out explicitly to IPT later. We can invoke IPT from the command line and pass the source code in as an argument by typing IPT, then the path to the file. IPT first prompts the user to select a parallel programming model. We will be using MPI for our parallelization, so we will select option 1. Next, IPT will ask which function the region for parallelization is in. We will select option 1, which is main. There are many parallelization patterns we could choose from, but we will select option 1, which is for loop parallelization, because this best fits our need. Next, IPT will show the user possible for loops for parallelization. This is not our targeted for loop, so we will tell IPT no. IPT will show the user the next for loop, and this is our targeted region, so we will tell IPT yes. Recall that the variable solution num is being reduced. We will select option 4 since this is solution num. We are using summation for this reduction, so we will select option 1. We want to send the results to all processes, which is also option 1. Now we are basically done with parallelization. We do not need to do this pattern again. We are not printing anything. We are not reading or writing anything. And we do not need to do any timing. Now that we have finished giving IPT information about our program, IPT will create a new file called rosecircuitsmpi.c. On the screen, we can see the results from the serial version of this program. The important thing to note is that 15 solutions were found. When running the code in parallel, we will want to confirm that this stays the same. Also, we can see that it took a little over 5 seconds to run the program. We will also compare the time it takes to run the program in parallel. To compile the file that IPT made, we will use the Intel compiler and the command mpicc rosecircuitmpi.c. To run the program, we will use the command time iRun_a.out. We are using 4 MPI processes to run this example. As expected, the number of solutions found was 15. Let's compare the time. As we can see, the program took a little over 2 seconds, which is about twice as fast as the serial version. Notice that the results printed to the screen multiple times. This is because each process is printing. We can restrict printing to only one process by telling IPT that we are printing. Recall that in the video, we skipped this section of prompts. Thank you so much for watching. If you would like more information or examples, please visit our website and user guides.